So I was asked by a student to just kind of review the concept of linearization, and so I wanted to come up with a problem, and I found one about estimating the fraction of 1.3 divided by 2.3. And I'm hoping this example will kind of allow me the opportunity to go over all of the really important stuff having to do with linearization all in one go. And so what I'm going to start off with is mentioning that I realize that 1.3 divided by 2.3 can be done in a calculator without too many issues. However, I want to kind of simplify this a little bit just because I realize that 1.3 divided by 2.3 is not going to be a pretty answer. Whereas, in reality, it's not always having this long, ugly decimal that I need to have. I might just need something approximate. I just might need something close that's maybe not so ugly. That in this case, this is going to be a really long decimal answer, and I'll mention that in a little bit. Um, so how about instead, let's use some calculus knowledge to see if we can find it at least a little bit prettier. So I'm going to use the function f of x equals x over x plus 1. And the reason I'm choosing that function, and I want to think about it from this perspective, is let's just imagine if I use 1.3 as my x value, then in the denominator, x plus 1 is 2.3. So the idea, if x is 1.3, kind of holds with this fraction that I'm trying to estimate. And so what I'm going to do is I'm going to choose an a value, a focus point, that is a little bit easier to calculate than maybe 1.3. So I'm going to choose something close to 1.3, and I'll just use 1. And I'll treat that as my focus point. And by doing that, it should make it a little bit easier to do some of these calculations to at least get something approximate, at least get something close to 1.3 divided by 2.3. So a couple of things that I need right now. One of the things I need right now is the y value. I've already chosen a equals 1 as my x value. So my y value that I'll choose is going to be 1 over 1 plus 1. So I'm just taking 1 and I'm plugging into this function there. And 1 plus 1 is 2, so we'll use 1 half. Now, I could write that as 0.5. That wouldn't be a particularly bad idea. I just prefer fractions. They're nice and easy for me, so I'm just going to leave that alone. From there, I'm going to choose another color, and I also need to take the derivative. Now, if I look at my function up here, that is a fraction. That's a rational function, so I'm going to need the quotient rule. And so I'm going to choose the numerator as x and the denominator as x plus 1. Taking their derivatives, we get 1 and 1. Putting it back into the quotient rule, remember we're going to do f prime times g minus f times g prime over g squared. So it'll be 1 times x plus 1 minus x times 1 over x plus 1 squared. All right, let's do some math. 1 times x plus 1 is going to give me x plus 1. 1 times x is going to give me x. And those x's should cancel, leaving my final derivative answer as 1 over x plus 1 squared. Now, I still want to plug in that a value, that focus point. So I'll plug in f prime of 1 equals 1 over 1 plus 1 squared. We know that 1 plus 1 is 2, but then I still have to square it, so that's 1/4. So that's my slope. So I'm going to go ahead and start writing what my final answer is for that. So the linearization function looks like f of a plus f prime of a times x minus a. Well, we said f of a was 1/2. We said that f prime of a is 1/4. And we said a was 1. So there's my linearization equation. And what I want to do now is I just want to, again, give myself an estimate of what 1.3 divided by 2.3 is. And so what I'm going to do is I'm going to plug in 1.3 into my linearization equation. All right, so let's see what happens here. So we've got 1/2 plus 1/4 times 1.3 minus 1. 1.3 minus 1 gives me 0.3. And it might help to know that 0.3 is the same thing as 3/10. So if I do a little bit of arithmetic there, we're going to have 1/2 plus 3 over 40. That 1/2 is the same thing as 20 over 40 plus 3 over 40. And so a good estimate would be 23 over 40. And I can type that into my calculator, and I know that that's going to be a much prettier number than the actual value. So my estimate here, and I'll write it down real fast, is 0.575. Okay, and that is my estimate. Now, again, I realized that I ended up using a calculator there at the end, but it sure beats having to write down, and let me go ahead and do 1.3 divided by 2.3 on my calculator. 1.3 divided by 2.3 is the same thing as 13 over 23, but that decimal is 0.56521739130043, and it just keeps going. Now, this thing does repeat. It is a rational number, but that's not pretty. That I don't want to keep writing that down, and it just keeps going. Like I said, it repeats. It's a long decimal. So 0.575 is a much nicer answer um, than the actual answer. So the other thing that I want to talk about real quickly, and I'm going to choose another color. Let's choose this color, is percent error. So how far off is my estimate from the actual value? So what we're going to do is we're going to take L of x, which is the estimate that I wrote over there, minus f of x, which is the white actual answer that I got when I typed it in my calculator, and we'll divide by f of x. Now, two things. Number one, when I'm done doing this subtraction and division, we are going to make sure it's a positive answer. If it's a negative, just make it positive. And I'm going to also write it as a percentage. So I'm going to kind of round off that white answer. So 0.575 is my estimate minus, and I'm not going to write down that whole long decimal, so I'll round off 0.565. Let's do 217. And I'll do the same thing on the bottom, 0.565217 in the denominator. And so I'm going to go ahead and do this math. 0.575 minus 0.565217 divided by 0.565217 gives me about 0.017308. And again, I'm rounding that off, which is, if I move the decimal place over two places, 1.7308%. So 1.7% is not a bad error. I've seen many that are, several times bigger. So that's pretty close. It's pretty accurate. The other thing I wanted to mention, and I'm going to show you in a second, is just the idea of how good is an error going to be, or how good is an estimate going to be. And so what I want to do is I want to flip over and I want to look at the graph. So what I did was I went ahead and I already graphed um, this green rational function you see here. That is x over x plus 1. So as you can see, it passes through the origin and has this nice sloping curve over to the right. The blue line that you see here is actually the linearization equation, and I went ahead and I graphed it as well. Now notice right here where they intersect at 1 comma 1/2 is actually the focal point, the one that I chose because it was close to 1.3. And I want to zoom in. As long as I'm close to this focal point, as long as I'm close to that x value of 1 or that a value of 1, my answers stay pretty close together. Notice the blue line and the green curve are not all that far apart, no matter where I look. Even if I look right here at 1.3, those are pretty close together, especially if I'm considering it within the broad scope of, these y values over here on the side. Um, they're pretty close together at 1.3. Now, what happens as you move farther away? Well, the two things diverge. The blue line and the green curve get farther and farther apart. Same thing happens on the other side. The farther away you move from this focal point, this intersection, the worse our answers are going to get. So we want to choose A to be something close to what we want to estimate. That's why I chose A was 1 versus the actual answer that I wanted, which was 1.3. So hopefully this helps you guys better understand all of the aspects of linearization. Please feel free to let me know if you have any other questions, and I'll be happy to answer them.